Okay, so hello everybody. So for between now and the end of the semester, this is the way that I will be delivering your course content for Chemistry 151. And so for this first session, I'd like to go ahead and wrap up what we started last time, which is talking about chemical nomenclature. So that's the process by which we want to kind of basically identify a particular chemical compound, not only by its formula, but also by some systematic naming scheme. And so we have already covered several types of chemical compounds and their associated naming characteristics. And so if you haven't done so, make sure you go ahead and print out the handout that I have provided for you on Laudima. And so you can use this now for your review as well as for homework assignments, as well as later on, when we do have exams, we'll be able to refer to this as well. So remember last time we talked about the fact that since there are so many different kinds of compounds out there, millions upon millions of them, in order for us to kind of make it manageable within our class to be able to name a certain portion of them, we want to focus in on specific types of chemical compounds. And the one that we want to start off with are binary compounds. Okay, again, binary, as the name suggests, are compounds that will consist of two elements. Two elements. And there are different types that we've talked about, type 1, type 2, and type 3. So if you recall from the summary of the handout, type 1 binary compound are ionic compounds that will involve a representative element in terms of a metal that will combine with a non-metal. And these representative metals will always have a fixed charge. So for example, all the alkali metals from column 1, all the alkaline earth metals from column 2, as well as aluminum will always have fixed charges. So alkali metal always +1, alkaline earth metals always +2, and then aluminum always +3. And then when they combine with nonmetals, and nonmetals will have a certain negative charge that they will tend to form, and you can actually see them on the periodic table and figure out what charge they're going to have. And what will happen is that for this type 1 type of material, they will always form in a way that the charges balance out. So if you look at it in this example, if I have, let's say, sodium, which will always form a +1 charge as it combines with, let's say, chlorine, which then becomes a negative 1 chloride ion, then when they combine, they will always combine in a 1-to-1 ratio. So there's only one possible formula that it will form when you have a type 1 binary ionic compound. So in this case, the naming scheme is relatively simple. All we do is we name the metal, the name of the metal, they always come first, and then we name the anion with the IDE ending. So this would be sodium chloride, for example. So this is just a quick review of what we did last time. Of course, there are going to be certain kinds of metals that will not always have the same kind of ionic charge. So for example, aside from the first two columns and aluminum, things that are in the transition metal range, for example, when you look at metals like iron, copper, nickel, and so on and so forth, it is possible for them to have various types of ions that they can form. So iron, for example, can form either a +2 charge or a +3 charge. So when they start to combine with nonmetals like oxygen, for example, there are now two possible outcomes. So if I have an iron +2 charge combining with oxygen with a -2 charge, they will always form then a 1-to-1 combination, so one of each. If I have, on the other hand, iron +3 and oxygen -2, in this case, in order for the charges to balance out, you would now have to have 2 iron with 3 oxygen in order for that to happen. And so again, the process by which we determine the subscript basically was covered last time. So if you're not too sure, make sure you go ahead and review that as well. And so now, in order for us to name these, we have to now be able to specify which of the ionic charge we're talking about for that particular metal. So we use a Roman numeral. So this would then be called iron 2 oxide. This is iron 3 oxide. Again, be very careful. We do not use the Roman numerals to associate with the subscript. A lot of people make that mistake. So this is not iron 2 oxide, for example. So again, make sure you recognize the fact that this Roman numeral refers to the charge on the ions themselves. So that's going to be something you need to keep in mind. So that's the second type, type 2 binary ionic compounds. Then we have a third type of situation where you have nonmetals combining with nonmetals. In that case, because you're not looking at balancing positive and negative charges anymore, you do not have to worry about charge balancing. Those situations, you now just basically have to keep track of the number of atoms for each of the elements that are involved in the compound. So for example, we can now have things like the carbon and oxygen coming together in a 1-to-1 ratio, or carbon coming together with 2 oxygen. In this case, we use prefixes to designate the number of atoms per element. So in this case, if you check again with your handout, there is a short reference table here that will allow you to pick up all the prefixes that are associated with the actual counting. So in the case of the fact that if I have one carbon here and one oxygen, okay, if there's only one atom for the first element, we do not need to use a prefix. That's the only time you don't use a prefix for naming. Okay? Otherwise, you always will have to have a prefix in front of the element. So here we just call this carbon. So we just use the name of the first element, and then we use the anion name plus the prefix to tell me how many atoms there are. So in this case, this is carbon monoxide for one oxygen. This is now carbon dioxide. So again, if you are not quite familiar with that, make sure you review some of the things that we did last time. Okay? And then, once we have all three of these types, we then move on to the possibility now of expanding our horizon, so to speak. So instead of just now naming binary compounds, we can now try to name compounds that will have more than two elements. In this case, we're going to, again, specialize in a particular subgroup of everything else. In this case, we're looking at compounds that will include polyatomic ions. And polyatomic ions are nothing more than clusters of atoms coming together as a group and having a net charge associated with them. And they will be moving around, so to speak, as a single unit. In this case, what you find is that for most of the polyatomic ions, as listed on this table here, you'll find that almost all of them are going to be negative anions, with a couple of exceptions. The two exceptions that you see, again, as we mentioned, is going to be H3O positive, which is the hydronium positive anion, and the NH4 plus, this is now the ammonium. Okay, so the hydronium and the ammonium are the only two positively charged polyatomic ions that you probably encounter. Almost all the others are now going to be negative anions. Okay? And so what you find is that in this case, because now you're dealing with ions again, okay, these polyatomic ions can now combine in a form that will allow them to cancel charges from each other. So when you have a positive ion, whether it be a single metal or whether it's one of the two polyatomic ions that we talked about for the cation, then it will combine with some sort of anion, whether it's a singular anion from a single element or if a polyatomic anion, they would then combine together in the same way as type 1 and type 2 ionic compounds. And so we use the same naming scheme. So if, for example, one of the representative metals, like anything in the column 1, column 2 aluminum combines with the polyatomic anion, all you have to do is now use a special name associated with the polyatomic anion. And the names of these polyatomic ions are, again, listed in the reference table here. So make sure you make use of that. So for example, if I have sodium, combining with the polyatomic ion NO3 minus, in this case, when you look at this, you're saying, well, sodium will always form a +1 charge, so now that's your positive cation combining with a negative polyatomic anion. Because they both have the same quantity of charge, +1 and -1, we can now combine to form NaNO3. So to name this, all you have to do is first recognize the name for your metal, in this case is sodium, and then the second one, of course, is now your anion over here. So this is now going to be sodium. Now all you have to do now is look for the specific name that's associated with this particular polyatomic anion. This happens to be nitrate. So basically, this is now just called sodium nitrate. It's pretty straightforward. So the idea is that you want to make sure that you are able to utilize your references to kind of help you make those decisions as to how to name these things. So for example, I've also provided you with a little flow chart like this that allow you to kind of flow through and make decisions as to which of the rules to apply up to this point. So for example, the very first thing you should ask yourself is when you're given a particular chemical formula, ask yourself, is it a binary compound? In other words, are there only two elements in there? If the answer is yes, there's only two, then you follow the flow chart from here to the next part, which then asks your second question. So if you have a binary compound, first of all, are there any metals present? If there are metals present, then you follow the chart to another decision where the next question then, what kind of metal is it? Does it have more than one possible charge that it can form? If the answer is yes, then what you have is you have a type 2 ionic binary compound. So in that case, you can then use the rule for naming 2, using the Roman numeral to designate the charge on the metal. If no, it does not have multiple ionic charges. If there's only one, then it's pretty easy. It's going to be type 1. So you just name the metal and then name the anion. It's pretty straightforward. Now, of course, if there are no metals present, then you use type 3, where you use prefixes to designate the number of atoms for each of the elements in there. On the other hand, if you do have a situation where you say no to binary, if it's not a binary compound, then what? Well, now the next question is, can you find polyatomic ions present in the formula? So in that case, what you're looking for is, very first thing you should look for is you look for a metal. That's the real nice one. You find the metal, you isolate the metal, and then everything else, then ask yourself, do you recognize that as being a polyatomic anion? So for example, if let's say I have, I don't know, maybe lead, and then I have NO3, let's say 2 over here, So in this case, the first thing you look for is that metal. Oh, here it is. There's that metal right over here. So you know that this is a metal. Then you look at the second part. This is now your non-metal. And now do you see this particular non-metal? This, if you look, you find that sure enough there is a polyatomic anion with the formula NO3 with a -1 charge. This is now the nitrate polyatomic ion. So now you know that this is going to be part of your nameable compounds. So now you apply the rule for polyatomic ions. So the first thing, of course, is you name the metal. In this case, lead. But here's the thing. In this case, lead is a transition metal. So now you have to, again, think about whether this is a difference between the type 1 and type 2 naming scheme. Whenever you have a transition metal, you want to make sure that you determine the charge on this metal. So the way you do it is you can kind of back things up a little bit. So if I were to write Pb up here, NO3 up here, I know that the NO3 is going to be a -1 charge. So that means over here, notice that the parentheses really groups the NO3 together as a singular object and tells you that there are 2 of those things. So that means there's 2 of the nitrate polyatomic ions. So for a total charge, you look at over here, 2 times a -1 charge giving you a net of -2 total on the negative side. Then to balance it up on the positive side, you know that you have to have a positive something here. You don't know what that is, But you also know that there's only what? 1 of them. So that means in this case, now 1 times a positive some number must give you a +2 that will then balance out your -2 over there. Then the question is, what is this number going to be? Well, obviously in this case, that must be a 2 over there. So you know that this lead must be a +2 ion. Another way you can kind of think about it is think about the crossover method. Remember we were talking about the fact that the crossover can allow you to use the charges to figure out what the subscripts are. You can do the same thing. In this case, just cross the subscript back over to get you the charge. So the 1 over here matches that 1. So that this 2 then must match the 2 over there. So you can use that method if you see that as a more quick way of getting your answer. But the idea in this case is now you need to tell me that this is the lead with a +2 charge. And so this is now lead 2, for example. And of course, the name in this case is going to be just the name of that polyatomic ion, lead 2 nitrate. So it should be pretty straightforward. Again, you have some homework assignments, the 2 worksheets that I've given you, so make sure you practice using that. And if that's not enough practice, make sure you do additional problems from the back of the chapter to get more practice from this. All right. Now, another thing you might recognize that when you're doing your homework, you might actually see some polyatomic ions that you may not recognize because they're not on the list that I've given you. So by no means is this particular list that you have from me complete. There are things that are not on here, but what you can do is you can figure out what those things are by looking at certain trends that you might see in the table itself. Before we get to that, what if when you look at a formula that is not a binary formula, that does not have a metal? Then what do you do? What if you see something like this? Let's say I have this particular compound. Notice in this case you have 1, 2, 3 different elements. So this is not a binary anymore. And you look, there's no metals involved. So what do? Well, in this case, you look for ammonium or hydronium. In this case, ammonium is the one that you see most often if there is a situation where there's no metal for a polyatomic formula like this. This one tells you, this is NH4 plus, the other one must then be NO3 minus. And so the naming for this is going to be just named ammonium nitrate. Pretty straightforward. So that should be pretty easy. All right, so again, make sure you practice Okay, while it might look kind of simple when I do it up here, when you actually struggle through it, on your own and practice it, it will become easier for you as well. So the next thing that we're going to do is kind of take a look at now the naming scheme itself. Notice that when you look at the polyatomic ions, that certain endings are very, very popular, so to speak, that they kind of occur over and over again. The idea of, for example, ITE ending, nitrite, for example, sulfite, for example, chlorite. And then there are other endings like ATE ending, 8, for example. So you have nitrate, chlorate, and so on and so forth. So the idea is that how do they then show any kind of particular trend that's going on that allow you to then determine whether it's going to be an IDE ending, or an ITE ending, or an ATE ending. So let's take a look at some trends that can now allow us to perhaps identify additional polyatomic ions and their associated names. The first thing to look at is the ITE versus ATE endings. Let's see what happens in this situation. What separates the ITE versus ATE endings? In this case, let's take a look at some easy ones. So let's start off with NO2 minus and NO3 minus. So if you look at the 2 on your reference sheet, this is the nitrite polyatomic ion. This is the nitrate polyatomic ion. So now with just these two, it might not be so obvious in terms of whether there's going to be a particular trend in there or not. So let's go ahead and try another one. What if now I use something like this? What if I look at another one that has the same 2 ending? So this time now, SO3 with a -2 and SO4 with a -2. And again, if you look it up in your reference sheets, this is now called the sulfite. This is called the sulfate. So now with this side by side, you now see an interesting trend. Notice that in this case, these are both polyatomic ions that contain oxygen. This one, nitrogen is basically combined with oxygen. This is sulfur combining with oxygen. And so you notice that the first part, the root of the name, actually comes from the non-oxygen element. So this is the nit for the nitrogen, sulf for the sulfur, and so on and so forth. Then really the IT and the ATE ending differentiate between the amount of oxygen that you have in the polyatomic ion. So for example, in this case, I have 2 oxygen for each of the nitrogen. I have 3 oxygen here for 1 nitrogen. That means that going from here to here, I've increased the number of oxygen by 1. And that 1 increase in oxygen is denoted now by a change in the ending from ITE to ATE. Same thing over here. I have 3 here connected to the sulfur here, and I have 4, 1 more than the 3. Therefore, the one that has a fewer oxygen will have the ITE ending. The one that has a greater number will be the ATE ending. And when that happens, you can now kind of use that to kind of guide your thinking when you encounter something that may not necessarily be on the sheet itself. So for example, if I have PO4 with a -3, that is something that's actually listed on your table as phosphate. So phosphate. But what if then I see something like this? What if I see something like PO3 with a -3? What would you call it then? Well, according to the same trend, then if this actually exists, this would then be the phosphite polyatomic ion. So you kind of use that now to predict other forms of polyatomic ions, if they do exist, or what they might look like in terms of the. Notice in this case, although the number of oxygen changes, the charge does not. The charge does not. So notice the charge is still -3 here, -2 -2, -1 -1. And again, the reason why these exist has to do with the idea of fulfilling the octets for the various configurations. So if you were to kind of draw the Lewis diagram for these, you can actually see that in these configurations, they will have a stable octet for all the elements involved. All right, so that one is the first trend that you might actually see. So that's pretty obvious. The next trend that you might be interested in is the situation where now what if instead of having just 2 in the series in terms of differentiating number of oxygen, what if you have something a little bit more? So let's take a look at the next trend. And in this case, we're going to look at the series of what we call oxyanions. As the name suggests, what do you think oxyanions are? Well, oxyanions obviously are going to be anions, in this case polyatomic ions that will contain oxygen. Oxygen. And in this case, they're going to be combining with other elements. And so let's start off with a very simple one. Let's say with chlorine. So I can have chlorine, for example, combining with oxygen. And when that happens, this can have a -1 charge. Then, interestingly enough, I can actually add another oxygen. I can still have a stable polyatomic ion. That will also have a -1 charge. I can continue all the way to here until I get to 4 oxygen for every one of the chlorine. So here now, instead of having just 2 in the series, I now have 4 different polyatomic ions in the same series, all with chlorine as the beginning and the oxygen as the ending part here. But they all have the same -1 charge. So in this case, how do we go about naming some of these? Well, as it turns out, this is not so bad because you already have the name for these in your table. So what you find is that in this case, this is called the chlorite, polyatomic ion. Now, going from here to here, this has 1 more oxygen. So from the previous trend, you can see, oh, this better be called the chlorate polyatomic ion. So that seems reasonable. We already knew that. But then what happens when I have even 1 greater or 1 less than the IT and ATE ending? Well, if that's the case, what we'll do is we'll go ahead and add a prefix to designate having more or having less than something. So in this case, the 2 that we're going to be using is going to be the hypo and the per prefix. The hypo and per prefix. You can think of hypo as meaning less than something, and then per is more than something. So that seems to be a reasonable way of basically addressing the naming scheme. So in this case, if I have chlorite over here, and I go to the previous one that has 1 less oxygen than chlorite, I would then use hypo in front, hypo in front of chlorite, and that would designate the situation where you have now 1 less oxygen than chlorite. So this is now the hypochlorite, the polyatomic ion. Going down to here, this is now 1 more oxygen than the chlorate. This is now the perchlorate polyatomic ion. So by the use of these 2 prefixes, I can now designate 1 less or 1 more oxygen in the series of oxygen ions. Now, of course, we don't have to stop here. Here's another thing. Once you have this series set up, then we call that, when we looked at the periodic table, one of the reasons why this is structured this way is that we basically group them according to similarities in physical as well as chemical properties. So everything that in certain columns, for example, belong to the same family that will have similar chemical properties. So notice that chlorine is in this column right here, second to the last column, and they belong to the halogen group. And so in the halogen group, all of the elements, fluorine, chlorine, bromine, iodine, and so on and so forth, have very similar chemical properties. So whatever one of them can do in terms of chemical reaction, chances are the other can do as well, based on the fact that they will have the same electronic configuration. So they all have basically 7 valence electrons around them. So all they need is 1 more to fill their octet. So because of that, what you find is that if chlorine can react with oxygen in this fashion to form these 4 polyatomic ions, then any of the other halogens should also be able to do so. And so that means it is very likely that I can actually have fluorine combining with oxygen in the same way. Fluorine with 2, fluorine with 3, and fluorine with 4 oxygen, all forming that -1 charge. So if I have this new series now of polyatomic ion that includes the fluorine, rather than chlorine, how do I name this? Well, it's pretty easy. Again, the first part, the root part, comes from the first element. So in this case, if this is chlorine and this is chlor, then fluorine would then be fluor, and then you use the ITE ending. So that would be your fluorite polyatomic ion here. And this would be the, obviously, fluorate polyatomic ion. And 1 more would then be perfluorate. And 1 less is hypofluorite. Hypofluorite. And again, you can do the same thing now, replace the fluorine with bromine, iodine, and it will work exactly the same. So that way you can now generate new polyatomic ions that were not on your table, and you will be able to find the proper name for them. And so you might have to do this for 1 or 2 of your homework assignment questions. All right, so that's the second trend that we can now see. Then we can move on to a third trend, the third trend, we'll see what happens when you add hydrogen to a polyatomic ion. So in the case of the polyatomic ion, let's say, for example, okay, so let's look at the effect of adding hydrogen to a polyatomic ions. Now, when I say adding hydrogen, I'm really looking at the fact that hydrogen has a tendency to lose electrons. Okay, so the idea is that when you put hydrogen there, it's going to drop the given electron, it becomes a positive ion, and so we're really looking at maybe adding H plus, okay, to the situation, see what happens. Okay, and so if I start off with, let's say, SO4 with a -2 charge, okay, this is called, of course, sulfate. Okay. Then what happens when I add a hydrogen to them? Well, if I add a hydrogen in front, SO4 -2, again, when I'm adding the hydrogen, okay, what you find is that the hydrogen will bring along with it a positive 1 charge. So what it does, it actually drops the charge by 1. So the -2 now just becomes a -1 charge, okay, -1 charge. Because the idea is that you're looking at a situation where in order for this to be attracted to it, you need to have opposite charges. So if I have a hydrogen ion somewhere that has lost an electron, it's now net positive. When it sees a negative -2 sulfate ion, it grabs onto it, gets stuck to it, and now it neutralizes one of the negative charge, and you have a net -1 charge at this point. Okay? In the same way, you can have CO3 with a -2. This is carbonate. Okay, and then if I put a hydrogen in front, that would drop the charge by 1 as well. Okay. So how do I go about naming this? Well, as it turns out, it's pretty easy. All you have to do is put the word hydrogen in front of your in front of your name. So this then becomes hydrogen sulfate. This is now hydrogen carbonate. Sometimes, due to historical reasons, people call this particular polyatomic ion bicarbonate, bicarbonate. And also, this can also be referred to as bisulfate. And for us, it's not going to be so important that we understand the reason behind it, but it just suffices to say that it is possible for them to be called bisulfate and bicarbonate at this point. A better one, of course, is just to use the hydrogen carbonate name. That makes it easy, much easier to kind of use as a standard for everything. Something we actually recognize, for example, if you see the fact that you have HCO3 minus, and if you have a sodium cation, these can now come together, and when they do come together, you have NaHCO3, the charges now balance out. Now, how do you name this? Well, this is now going to be your sodium, according to this, hydrogen carbonate. It turns out some of you might have seen this being called sodium bicarbonate. Okay, so that's also an acceptable name for this compound. Of course, you have this in your kitchen. This is nothing more than baking soda. Not baking powder, but baking soda. Okay, so this is probably the one that you see more often based on that particular substance. All right, but as I said, if you want to avoid confusion, we sometimes bicarbonate, sometimes gets us confused, say, well, there's 2 carbonate, so that could be a little bit tricky, so don't worry about that too much. Just use hydrogen carbonate, that's easier and much clearer. It is also possible for us to, let's say, for example, PO4 with a -3, okay, this is now phosphate, okay, so H, PO4 -2 is now going to be hydrogen phosphate. Okay, that's be obvious. But here's the interesting thing. If I add 1 hydrogen, what if I add another one? What if there's another hydrogen plus ion floating around, and it, again, gets attracted to this -2 charge and comes together with it? So is it possible then for me to have 2 of those connected to my phosphate? And the answer is yes. When you bring 2 of the +1 ions in, then you neutralize 2 of the negative charges, you still have a net -1 charge. So this is now going to be another possible polyatomic ion. So what do we call this thing? This one now is going to be called dihydrogen, 2-hydrogen phosphate. That seems to make sense. Okay, 2 hydrogen with your phosphate, forming this new dihydrogen phosphate polyatomic ion with a -1 charge. Okay? And you can kind of take this even further. Well, you can figure out, oh, well, if that's the case, is it possible then for a positive ion of hydrogen to come and continue to add itself to these polyatomic ions, and then what happens? So let's see what happens. So in this case, let's say I go ahead and this has a net -1 charge at this point, right? So if I have another positive hydrogen coming to here, what would happen if that is stuck to it as well? Well, this is what you would end up with. You now have H2SO4. But here's the catch. What's the charge on this thing? Well, if you look, okay, this has a -1 charge. If I bring another hydrogen that has a +1 charge, the +1, -1, they cancel each other out. So the net charge on this is 0. This is no longer an ion. So we do not need to name this as a polyatomic ion. So it turns out when this happens, this is actually a compound at this point, okay, that's neutral, and we're going to basically be naming that with a very special naming scheme later on. Okay, this is a type of acid that we're going to go ahead and name later on. So keep that in mind. So anytime you add too many hydrogen into the mix, you then neutralize your polyatomic ion, then you no longer have a polyatomic ion, you don't have to worry about naming it anymore. So this is the one that you can actually add 2 hydrogen because of the fact that this started out as a -3 charge. Okay? -3 charge. All right, so that's the third trend that we can kind of see. Okay, so the idea is that as you look at these things, you want to be sorry, this is a 4th trend. Yes, yeah, the 4th trend. Okay, so we want to be able to go ahead and make sure that if we see something that is not on the table, see if you can actually use one of these trends to recognize it and be able to come up with a name for it. Okay. All right, so you should now be able to do almost all the naming that we are giving you on your assignment. So let's take a look at some examples, just to make sure we can apply everything that we've learned. All right, the key here is this. The idea is that if you need to memorize some of these things, for example, if you want to continue in chemistry to a higher level chemistry class and so on and so forth, basically you really should just kind of look at the main ATE ending polyatomic ion. If you recognize and memorize all the ATE ending, from there you can then generate the ITE ending, and then the hypo and the per, as well as some of the other combinations as well. Okay, what happens when you attach hydrogen and so on and so forth. So basically things like nitrate, sulfate, phosphate, carbonate, chlorate, manganate, and chromate. Once you have those 7 memorized, then you should be able to derive almost everything else from that. Now, of course, there are a few that are kind of like by themselves, that are kind of unique, so to speak. So a couple of those, for example, you have the OH- polyatomic ion. This is the hydroxide polyatomic ion, and then you have the CN-. Okay, so this is the hydroxide. Polyatomic ion. Do not confuse this with the hydride polyatomic ion, as I mentioned before. The hydride polyatomic ion would then be what? Well, in this case, just hydrogen with no oxygen in it. So this is the H-. Okay, so sometimes, as we said before, hydrogen can actually act like a nonmetal and grab electrons as well. So if it becomes that, then it would then be the hydride. So this can now combine with a metal, for example, to form metal hydrides. This one is kind of interesting. This is one that's kind of neat. This is called a cyanide. Polyatomic ion. So notice that these are the exceptions to the rule that we don't have the ITE ending or the ATE ending. So these are the ones that are kind of like in the single elements forming anions. Right? And so in this case, the only thing that we recognize is the fact that there's no element with the root cyan, for example. So you know that it's not an element, therefore it's not that hard to kind of memorize this. And then hydrogen and oxygen before the IDE. Now it tells you there's 2 elements in there instead of the hydride, which has only 1, or the oxide, which has only 1. Okay? So hopefully that will help a little bit. All right, let's take a look at some examples. So let's go ahead. The whole idea is this. You should be able to now, when given a particular chemical compound, be able to come up with a chemical formula, as well as a systematic name that will then identify that particular compound. And you should be able to go back and forth. If I give you the name, you should be able to give me the formula. Or if I give you the formula, you should be able to give me the name. So let's do a couple. Let's start off with a name first, and then coming up with the formula. So let's try one. Oh, what's a good one? How about calcium phosphate. Calcium phosphate. So whenever you're given the name of a chemical compound, the first thing you need to do is, again, recognize the fact that if there is a metal in there, then you need to definitely be able to balance charges. If there's no metal to begin with, then you start thinking about prefixes and translating prefixes into a numerical subscript. So in this case, calcium. So the first step is to go ahead and write down the charge for each other part. So calcium is going to be a +2. Again, if you're not sure, check with the periodic table, look at where it is located, and that should give you a clue as to what charge it will be forming. Then the phosphate, oh, in this case, it is now the ATNA down. You know that this is going to be a polyatomic ion. So look for the polyatomic formula. That's going to be a -3 right there. So PO4 -3. So once you have them, then you go and combine them. Metal first, non-metal second. So CaPO4, and then crossing over, right? So 3 now comes down to here for the calcium. Now when the 2 comes down, make sure you put them in parentheses, and then put the 2 over there. Okay? So this is now your calcium phosphate, okay? Polyatomic ion, the polyatomic type of ionic compound. All right, so that one wasn't too bad. Let's try something else. Okay, so let's try something now that has, okay, something like this. How about tin 4 chromate? Okay, tin 4 chromate. All right. So again, each of these compounds will have certain purposes. The previous one, calcium phosphate is used for things like fertilizers and so on and so forth. In the case of this one here, tin 4 chromate, this is actually used for color agents in forming ceramics in China and so on and so forth. So that you can use this for coloring agents. So in this case, again, this is now a transition metal, or actually, a little bit beyond transition metal, and it is given a Roman numeral here. That tells you the charge on this particular element. So that means that for tin, it would be Sn. Okay, oops. Roman numeral 4 means that this is now +4. Okay. The next one, chromate. So again, this is the one that you can kind of go ahead and take a look at. The chromate is the CrO4 -2. Okay, so that is your chromate. Okay, so once you have that, again combining together, Sn. Okay, CrO4 crossing over. Notice in this case, if I cross a 2 over here, if I cross a 4 over here, I now have subscripts that are not in the lowest ratio. So I can now go ahead and factor out a 2 and give it the lowest ratio. In this case, this becomes Sn CrO4 2. And this is then be the correct chemical formula for tin 4 chromate. Okay, tin 4 chromate. Hopefully those 2 examples are good. Let's try one more. Okay. This time, let's look at what happens when we have, let's say, the following. What if we have? Oh, here's an interesting one. Okay. Dinitrogen monoxide. Okay. In this case, when you see the dinitrogen in front, it's not a metal anymore. We're now looking at a type 3 polyatomic ion, type 3, okay, binary ion compound. And so no ionic charge balance needed. You just look for the prefix. So here you have a di prefix and you have a mono prefix. So that means that for nitrogen, you need 2 of them. For oxygen, you need just 1. So N2O would then be the chemical formula for dinitrogen monoxide. Okay. So once you have this, again, you can now go backwards. Okay, given a chemical formula, you should now be able to come up with a name for it. So let's try one over here. Let's try this one. Cu. Okay. So this looks a little bit tricky because it's kind of confusing. So let's see what happens. In this case, let's kind of ask ourselves, is this a binary compound? Well, I have copper here, carbon, hydrogen, carbon, oxygen. So obviously more than 2 elements, this is not a binary compound. Okay, so right away say, okay, not binary, it's not 1, 2, or 3. Okay, so the next thing, of course, is that are there any polyatomic ions in here? So right away you see, oh, wait a minute, I have a copper in here, so that looks pretty good. But then when I look at this, you have your CH3COO. If you look for that in your table, you don't find it. Well, as it turns out, the reason why they write it like this is because it makes it easier for you to visualize the molecular shape. And that's why you kind of write it like this. For those of you who took lab, you find that it really is very helpful when you see it like this to be able to draw what this particular molecule looks like. But what you can also think about is the fact that this is nothing more than telling you the number of atoms per element. So you can just combine it back together. So if I were to take carbon, I see, oh, I have 2 carbons over here. That's really C2. And then I have 3 hydrogen and then 2 oxygen. So C2H3O2, wow, I wonder if I can find it in that table. And if you look, sure enough, there it is right there. C2H3O2 with a -1 charge. This is now your acetate, okay, polyatomic ion. So that means in this case you have acetate here, you have copper here, and this will have a plus, okay, charge, but we don't know what that numerical value is. So now we can go ahead and ask ourselves. In this case, I have one of these, okay, with a -1 charge, and I have one of these, so that means this must then have a +1 charge for it to balance out properly. Since it's combining 1-to-1 ratio, 1-to-1 ratio. So if that's the case, and this is now going to be copper. Remember now, the charge 1, okay, acetate, copper 1 acetate. Alrighty. So again, given the chemical formula, we should now be able to, okay, come up with a name for it. Let's try one more. Let's try one more. So this looks like. That looks pretty complex. Okay, 14 atoms together, but I don't have a metal. So this is really just a type 3 binary, non-metal, using prefixes. So this is 4 phosphorus, so 4 is tetra phosphorus. Now this is 10 is deca, but because oxygen is what follows it, we cannot drop the A. So this is decoxide. Okay? So tetraphosphorus decoxide. All right, so hopefully that kind of helps to kind of illustrate some of the technique and some of the decision making that you need to do for naming these chemical compounds. So the last topic that we want to have for this particular part of nomenclature is look at naming a specific kind of substances. In this case, we're going to learn how to name acids. And acids are a very important group of substances, very important group of compounds, and they are very specific in that they have certain characteristics. We all know what acids are like. For example, they have certain physical characteristics. They tend to be sour to taste, for example. Not that you want to taste all the acids out there, but there are certain acids that we actually ingest in our food, and so we know that acid like vinegar, for example, tastes sour. So that's a characteristic of acid. Another characteristic might be that it can be quite corrosive. Okay, so it's kind of caustic, so that if you get it on your skin, it can actually burn, and it can actually corrode metals. So if you put metals in acids, like aluminum in acid, for example, it will actually cause the metal to break down. And so we have certain characteristics we can associate with acids. But before going into that, we just want to look at the definition of what an acid is. So what constitutes an acid? In general, an acid is a compound or substance that when dissolved, will give up a hydrogen ion. In other words, a proton, for example, H plus, or proton. And so basically, if I were to look at a very simple substance like hydrogen chloride, more likely when you find this is going to be in a gas form. So these are molecular particles that are moving around, hydrogen chlorine stuck together as a single unit, usually in the gas. But what can happen is if you take this gas and you kind of bubble it through water, water, as it turns out, has a very interesting property in that water are polar molecules, as we discussed before. Being polar, it has two ends, one positive, one negative end. And so what can happen is that the negative end of the water molecule can now start to attract the positive hydrogen ion over here. And the positive end of the water can now start to attract the negative anion on the chloride side. And so as they begin to stick together, they can then pull them apart. They kind of act like wrecking crews, for example. You can imagine a demolition team, for example. Their special job is to just break things apart. And so anytime you have ionic compounds, when you put it into water, we see that water has the potential of dissolving them, that they can dissolve in water. And this is not the same as melting, as we said before. So dissolving is special in the case that you put it into a fluid of some kind, like liquid, like water. The water has the ability to kind of break them apart. And so what happens is that when you break them apart, you now end up with a hydrogen ion sitting by itself. You have then the chloride ion by itself. And of course, these guys are surrounded by water molecules here, surrounded by water molecules here. And of course, we give that a very special designation. We say that the HCl now is in an aqueous form. Aqueous form. So whenever you see this AQ here, just think, oh, it has been dissolved now in water, so that I can now look at them as separate ions. Now, of course, with these guys in the water, they also have a possibility that they might come back together and find each other again and create a bond all over again to form your HCl molecule again. Well, as it turns out, depending on the kind of material that we see here, the ability for them to come back together can vary dramatically. For HCl, for example, even if they try to come back together, they get pulled apart very, very quickly again. So you very seldom have any of these types of molecules floating around in the solution of water and HCl. Most of the time, you just see them as them by themselves. So whenever you have a solution where by putting a particular compound in there and you're allowing it to dissolve almost completely, where most of them now have been turned into these free-floating ions, we see that we have basically a strong acid. So HCl is a type of strong acid we can have. Other kinds of acid that also can produce hydrogen, ions, will basically have a situation where the molecules come back together, and in the water itself, very few of them have been taken apart, and only just a couple maybe, out of several hundred or even thousands. And then what happens, of course, is that most of them are still moving around as a molecule, then we call that a weak acid. So in other words, we can kind of measure the strength of an acid by the concentration of this ion floating around in this form. The higher the concentration, the stronger the acid is going to be. Later on, we'll actually designate strong acids and weak acids and give you a list of what they are. But for now, suffice it to say, this is what we're looking for when we say acid. Now, as it turns out, it's not quite exactly true. What you find is that with this hydrogen ion, as it flows around, it doesn't really hang up by itself. There's a good chance that this will actually grab a hold of a water molecule and basically come together with them. So you can imagine now H2O combining with this H+, you add this to the H2O, you now end up with H3O. Oh, wow. That should be familiar now. This is actually now the hydronium ion. So this is now the hydronium polyatomic ion. So basically, another way you can think about defining an acid is that it is any compound that when dissolved in water produces hydronium ions, floating around. So that's the definition of an acid. So with that in mind, we now want to go ahead and come up with a naming scheme as to how to name these different kinds of acids. Now the book goes into a lot of detail in terms of differentiating between different kinds of acids. For us, we're not going to worry about it as much. We're just going to go ahead and look at some very simple way of separating them really quickly and then be able to come up with a name very quickly. And so the idea is this. Whenever you have an acid, again, you always have to have the hydrogen ion. So chances are when you look at it, you see an H right in front. So things like HCl, for example, or HF, Or sometimes the hydrogen actually be combined with polyatomic ions as well. You actually have HCN, for example. And again, as we said before, in order for it to be designated as an acid, we need to have them in the dissociated form in terms of individual ions. So if I just put it like this without any designation as to what form they're in, most of these are going to be just molecules floating around. So we want to make sure that we designate them as acid by putting in the AQ or aqueous designation. So whenever you see this, then you know, okay, it's going to be an acid that we're going to be interested in. So this always has that hydrogen in front. On the other hand, if I do this, AQ, is this an acid? Well, the answer, of course, is no. In this case, although this is an aqueous ionic solution, that means the sodium and the chloride has been separated by the water, there are no hydrogen ions floating around, there's no hydronium floating around. So this is not an acid. So be very careful. Always look for that H beginning. Sometimes you even have things like this. So it is possible for you to have more than one hydrogen if the polyatomic ion has a greater than negative 1 charge. So in this case, this would have SO4 we would have minus 2, so you have 2 hydrogen before that SO4, and so on and so forth. So when you break this up, you now have more than 1 hydrogen can actually possibly come off of this. So notice in this case, or if I have another one like this, H3PO4Q, and so on and so forth. So all of the beginning part, the H, would then clue you in on whether or not you have an acid or not, and then whatever comes on the anion side would then designate how we are going to go ahead and name these acids. So I'm going to show you a quick flow chart as to how to decide what to name these acids. So in naming acids, you need to ask yourself the following question and make the following decisions. The first thing you're going to do is ask the question, does the acid contain oxygen? That's the first question. Does it contain oxygen? If the answer is yes or no, then that will decide how you are going to proceed next. If the answer is no over here, or if the answer is yes over here, we then have different choices that we can make. If the answer is no, then the way we're going to do this is the following. Okay? I'm going to go ahead and start with hydro. Okay, so start the name with hydro, and then we're going to add on to it, okay, the root part of the anion. Okay, so whatever the root part, that is determined by the anion that follows it, whatever that might be. And we add on to it IC ending. And then, of course, the last thing is calling this an acid. So hydroic acid. Okay, so what does that look like? What does it look like over here? These 5 acids over here, these first 3 do not contain oxygen, while these 2, okay, does have oxygen. So that means that this can now apply to any of these guys over here. So that means in this case, this is now going to be hydro, and then for Cl, okay, the root is then chlor. Then we have the IC ending acid. Okay, so here's the hydrochloric acid. That's the combination. So same thing with over here now. This would then be the hydrofluoric acid. Hydrofluoric acid. So the hydro is only used, okay, when there are no oxygen in your acid itself. And of course, be careful. Don't confuse hydro with hypo. Sometimes people get that confused. Hypo and hydro are not the same thing. Be careful not to confuse them. This is kind of interesting. Okay, in this case now, you still have hydro. Okay, so what is this? Well, this is cyanide. Okay, so this is cyan. Okay, ic acid. Okay, so hydrocyanic acid. And then as it turns out, there's only so many, okay, acids that you can have without the oxygen. So if you want to, you can actually just go through the whole periodic table and go through the whole polyatomic ion table, pick out all the anions that have no oxygen in it, and okay, create the names so you know what they all are. Okay, so those are pretty straightforward. All right, so once we have that, okay, then we have our other option where we have oxygens themselves. Okay, and in the textbook they actually give these a particular name. Okay, so for example, when you have the anion with oxygen in it, we call those the what? Oxyanions. Okay, if they are called oxyanions, guess what? The acids are now called what? Oxyacids. Okay, oxyacids with oxygen in them. So in this case, if the answer is yes, then interestingly enough, there is now going to be a split between 2 possible cases. Okay, 2 possible cases. In this case, we do not use a hydro prefix anymore. We're just going to go ahead and go directly into the anion naming. Okay, so the first thing is we take the root. We're going to use something. Yeah, let's use this one. Okay, let's use this one. Okay, so we take the root. Okay, and in this case, the root depends on the anion itself. Okay, so let's take a look. So for the root, I should say, let's take a look at anion. Okay. The anion, if it ends or ending in ITE. Okay, so if we look at the anion, we look at the name of that anion. If that anion ends in ITE, then we're going to use a root of anion. Okay, so that's the root of the anion, and we're going to add on to it an OUS ending, and then acid. Okay, so if it's ITE, okay, it becomes OUS. I to us, for example, okay, and that would then be the acid. On the other hand, if the anion ending in ATE, okay, ATE, then again we use the root of anion, add on to that the IC ending, and then acid. Okay. So let's see what happens over here. So for these two, okay, it's H2SO4. SO4 is the sulfate polyatomic ion. So if this is a sulfate polyatomic ion, that means now this is the AT ending. I'm going to use the root of your anion, which is the sulfur, okay? And then, in this case, IC ending, and acid. So this is called sulfuric acid, sulfuric acid. This one over here now, okay, this is now the phosphate, okay, polyatomic ion. So this then becomes phosphoric acid, okay. So sulfuric acid, phosphoric acid. Okay? So the phosphate, sulfate. So this, interestingly enough, this kind of goes back to the original element, okay, in front of the oxygen. So phosphorus is sulfur. Okay, so those are where the roots come from, not from this name, but from the original, okay, element before the hydrogen. So that means I can also now have this, for example, if I have now, let's say, H2SO3 AQ or HNO2 AQ. Let's see what happens in that situation. So here, SO3 minus 2 is now the sulfite ending to your polyatomic ion. So that's your first option there, so ending ITE. So now the root is still sulfur, except now we use the OUS ending. So this is now the sulfurous acid. This is now, of course, okay, NO3 is the nitrite. Okay, so again, ITE ending. So this is now the nitrous acid. Okay. So ATE, IC, ITE, S. So IS, ATE, IC type of change. Okay. And again, once you look at your polyatomic ion list here, you can then use that to, okay, decide which of these cases you have. Most of the time when you have the polyatomic ions, it will be either one of these, ITE or the ATE ending. Okay. Any questions? Oh, unfortunately you can't ask questions here, so I will be setting up Zoom meets that we can actually get together as a class and you can ask questions at the time if you have any questions regarding what we talk about here, as well as from the homework assignments and so on. Okay? Right, so this is it for now until the next session. Okay, bye.